All right, so hello everyone. My name is Lu. I'm a lead distinguished scientist from Verizon. And Mike is my colleague here with me. We are very excited to present large-scale pathway recommender system at Verizon at Resummit today. So here's an overview of the agenda today. So at first, we're going to talk about the different recommender use cases here at Verizon. And then we will talk about the new generative recommender architectures Verizon has been using in the production. And we're also going to talk about how we accelerate our GRAC model training with the help of the Ray. And at last, Mike will talk about the responsible AI practice here at Verizon. So first, we will talk about the different recommender use case. So Verizon being a telecom, we actually have lots of different recommender use cases in production, right? The first category we put is kind of product-based, right? So it's really very similar to the common e-com or retail-based product recommender, right? Things like our homepage, right, where we are showing different device as recommendation to our customers. And also we have cross-sell-based accessory recommender, right? Also we have places where we display product alternative, leverage the similarity model. And we also have build bundle for customer sections where we display kind of a different product, right? What goes well together as a bundle recommender, and a lot more, right, under this category. And second category, the plan-based, I would say, is more kind of industry specific, right? So it's mainly focused on the about your phone plan, right? So based on the usage, right, like what service need or not need, we kind of give our customer recommendation of the plan, right? What best based on their actual usage, right? And also this year we launched this new kind of customizable plan, what we call the My Plan, where customer can pick and choose different perks, right? Like Disney bundles, right? Like Walmart Plus, right? It really depends on the customer usage, right? So that's like another example under plan recommender. And we also have a lot more than just the two, right? So in here, we just listed like a few here, like how we recommend offers to our customer, right? Loyalty-based and some others, right? Offer related. And also our service, right? So Verizon has this Plus Play program where it allows user to subscribe different kind of services, right? Things like Netflix, Max, right? Those popular subscription services, right? We have this Plus Play as one-stop shop for the user to pick and choose from, and that's like another big examples, right? Also, we have services beyond just wireless service, like home internet, right? Like files, TVs, and that's like another example. And also, we have lots of places where we have search functions, right, on our app, on our website, and that's also where we have those recommender use case, and of course a lot more, right? We just put a few examples here. And here's like another view we can look at it, right? So given by any use case we mentioned above, right, we kind of can break it down by even further, right? So first level we typically look at is which channel customer interact with us, right? So common places like website, mobile app, retail store, and we have a lot more, right? Like telecalls, like call centers, right? Like there's a few more, like customer can interact with us, and at a high level we kind of can break down customer by, let's say, prospect, right? Like a new customer or like existing customers, right? And also we have flow-based, right? Like where we treat kind of a different flow, slightly different, right? Experience-wise, we have a new user, right? A new user coming and trying to shop with us, right? We kind of call that new user flow. And we have upgrade flow for the existing customer, right? Which, who looking to upgrade their device. And we also have like add a line base where it's kind of, adding new lines, right, to their account. That's another example. And the last, we look at the task, right? So when we say task, we're really talking about the optimization goals, right? Things like click-through rate, right? Click-through conversion rate, add to cart rate, right? Conversion, just being a few examples here. So the point here is it can really go very deep, right? Depends on like which use case we're talking about. And here is a deep dive view, right? So let's just use a common what we call the grid or device recommender, but that's really kind of the homepage of the a smartphone homepage, right, at Verizon, right, where we call that grid war, but it's just a way for us to display different devices to our customer, right? So we call that grid war device recommender, and use that as an example, right? So let's say we are looking at the website, right? So the channel can be a website here, right? And customer time, let's say we are targeting for the existing customer only, right? And flow-wise, we are looking at the upgrade flow, where customer already have a device and looking for upgrade, right? Let's say a new iPhone, like customer looking for upgrade, that will be fall into this flow. And the task, right? Let's say this use case, we're looking at homepage, right? Like who we want to drive higher kind of click-through and also conversion, right? So let's say that's a task. So this is just a specific example, right? How a use case can fall into this kind of a larger category. And you see, right? It can also expand. Let's say we also want to take care of the airline flows, right? And traditional approach has been build maybe a separate models, right? Or like a separate pipelines to maintain that, right? And that's kind of the previous approach we were taking. And here, just taking through kind of another view on the recommender use case here, right? So let's say, looking from the customer journey perspective, right? So customer, let's say, started by interacting with the website, right? Let's say customer trying to search folding phones, right? And then later they can, start checking things again on their mobile app, where we have the personalization supplies, right? To kind of showing, right, the personalized device grid words on their phones, right? Which can reflect their website behavior, right? The fold phone search behavior. And as they go down through the funnel, they can see the customizable plan recommender, where we're showing different perks, right? They can add, right? As part of the flow. And also, of course, across our accessory recommendations, right? Where we are showing different accessories compatible with the device they're interested in. And last is, it can be customer goes to the retail stores talking with sales agent, and you see those experience being carried over to their sales agent, right, where it can help them better serve our customer. So that's just like another view. So next, we're going to talk about kind of this new kind of common foundational modeling approach we're taking, which we call the generative recommender, right? Or later we can refer as GREC. So the few highlights we put here is like, one is, of course, generalization, right? So it's basically, GREC is able to generalize across a variety of different recommender tasks, right? So it has like high capacities, right? And high generalization, where, traditionally we may need to build separate models to handle. Now, we can use this kind of, GREC, architecture to handle like multiple tasks at once, right? And second part is obviously the mixture of experts, right? So the key for us to scale the GREC is applying this, mixture of expert architecture, right? Where we can really scale modeling out without kind of lose efficiencies here, right? And also here we have a new kind of task sentence-based routing strategies. So it particularly efficient, right, for the recommender scenarios, right, in the real world application. So here's kind of like one view, right? How kind of we are, building these models, right? So we are taking two use cases as an example, right? Previously, at Verizon, we kind of treat add-a-line and upgrade slightly different because it's just, to business-wise, it's very different flows, right? So we kind of, use different approach to build the recommender model. But now under GREC, they kind of, being as one kind of entity, right? So the way we handle this is we use this shared architectures, right, to take both use cases into the same model, right? And in here, we have this router structure where it basically has dynamically routing, right, different input into the corresponding experts, right, during the training time, right, to find out the best experts. And then the output kind of, back to the shared layer, and it kind of able to kind of showing use case specific output, right? Depends on different use case we are inputting here. The key architecture here is this router, where traditionally, let's say, some common like architecture is like letting the router just looking at all the tokens, right, getting as input, and for router to route like each token separately, right? The issue with that is it's kind of taking lots of computation, resources, right? Let's say if the token length is very long, then this router kind of, it become expensive, right? And also it's become kind of unpredictable because it's kind of depends on the expert setup, right? It kind of can increase the training and inference time there, right? So what we did here is basically we extract the task info kind of out of the input, right? And so the example here, we're kind of looking at two task info, right? One is our objections, right? Is it trying to optimize on click-through conversion or something different, right? So that's like one primary task, right? And the second task is kind of the flow, right? So which flow we are looking at, right? Is it like add a line or upgrade? And router is actually only looking at these two tokens, right? So based on these two tokens, router make a decisions, right, to routing this holistic input features from shared layer into different experts. It has two benefits, right? One is it's a lot faster, right? Because instead of like looking at the entire token from the input, it's only looking at the task tokens, right? So it's very efficient and kind of it's not gonna increase, right? Like as we growing our features here. Second is it's very predictable, right? In terms of given by a task, we already know, right, what expert will be leveraged, right, to handle the prediction, right? This provides additional flexibility when we deploy these common models into the use case. We have the option to pick and choose subflows, right? So we already know, let's say, upgrade and add a line only will pick certain experts. So we can extract those experts and only deploy those experts into the use case, right? So it can reduce to a much smaller model size and faster efficiency there. So that's kind of the task-based routing strategy we apply here. Here's like a zoom-out view for the GREC, right? So I think first talk about the left side a little bit, the wide and deep hat, right? So this is a kind of a classic wide and deep setup with a few enhancements here. One is aside from the common wide and deep features, we also have this pre-trained transformer hat to looking at the search, right? So because customer does search a lot on our site, right, trying to find different plans, asking questions, looking for a specific device or accessories, it's a very useful input, right? So in our case, we essentially we have a dedicated search transformer encoder to handle those search tokens, right? So that's part of the wide and deep hat here. Another is kind of how we are handling the cart, right? Because we think users' current cart speaks a lot, and our model really need to handle that. So what we did is we use behavior to train the item ID-based embedding, right? And to compensate for some items not that popular and we don't have enough behavior data, we also apply this kind of metadata level kind of features, right, to compensate. So we have this item categorical features and numerical features, just to help with the code embedding problem a little bit. And on top of that, we also have this cognitive-based item learning, where we apply this transfer learn clip encoder to learn from the item image and description directly, right? This is also kind of compensated around the item ID learn from the behavior, right? To ensure like even given by a fresh item, this model can behave, reasonably well there, right? So that's kind of on the wide and deep side. And the right just a zoom out view, right? So we're kind of together with this wide and deep, we have this sequence hat where we looking at customers' behavior, right? How they interact our different channels, right? Kind of in a sequential order. We have this parallel transform architecture set up to learn from different sequence, right? And also we have this task ID-based input, right? To help with our MOE routing strategy. So that's GREC. And also as the model size grows, right? Like it's become particularly important, right? We, the entire training setup become very important, right? As now we have larger models to manage and train. So we accelerated the GREC training a lot with the help of the Ray, right? So it kind of, at a high level, we break it by two parts. One is obviously the Ray parallelism, right? So we're kind of using a old image encoding step as an example, where let's say without the parallelism, it takes a long time, right? Even just on the legacy CPU-based machines, right? It takes a very long time, one by one, kind of handling the image to finish this encoding, right? We're applying the Ray core. We're able to leverage all the CPUs we have, right? And you see this encoding step, significantly improved, right? And the second part, kind of this hyperparameter tuning step, where G-Rack has lots of parameters, right? Where traditionally we're kind of using just manual kind of parameter tuning, where it takes a lot of time to do, and it's very hard to kind of embed that into our pipelines, right? And also it's as a model is big, right? It's just inefficient to manually select and run through the full training to find out which one works best, right? So with integration of the Ray here with Torch Lightning, we're able to kind of parameterize, right? Kind of this step. We're just showing an example here where we can easily define the search space, right? Using our parameter config files, and we can use the HR scheduler. This is just an example where it's a quick setup, and then we can run the Ray tune, right, to start searching this space, right? Like instead of like manually define and save the model and do the logging like everything manually. So we see lots of success by just start using this more kind of integrated hyperparameter tuning flows here. So next I'll hand to Mike Tan to talk about the responsible AI practice.
Thank you, Luke. Hey guys, I will just spend a few minutes to talk about the responsible AI stuff related to the personalization engine. At Verizon, we have an inspiration to be the gold standard of responsible and transparent use of AI in the telecom industry. For that inspiration, we actually started building our responsible AI program in about 2 years ago. Instead of building that just like another governance or compliance function, we look at responsible AI as a capability to combine like best practice, skills, technology, and change behavior. Because we are using AI for hyper-personalization of a lot of our solutions, and we have a lot of customer data. So in order to serve our customer using this AI solution, we must go hand in hand. The personalization AI must go hand in hand with our responsible AI practice. So here you see a overall workflow that like every single model at Verizon going through today. Then you see that starts with the review of the use case, and then we follow that with a risk assessment. So through the risk assessment in Verizon, we will know exactly the harms and benefits of your AI solution and what you need to watch out for. And then we will bring in the expert to provide the guidelines during the design and the development. And then also all the features, as you can imagine, are also reviewed and vetted by our legal counsels. And our team will also help the development team to do a lot of bias testing and mitigation to make sure the models are not generating any disparate impact, because we are using a lot of our models to determine eligibility of our services and our plans and services. So it's very important to make sure the models are not generating disparate outputs, right? It's more so important today when we are all using behind the scene the large language model to understand the natural language people use to ask our chatbot and ask questions, and that the bias that may embed in any of those large language model is not going to be further propagated downstream to our other machine learning models. So the workflow here helps that we have the ethics by design for our AI models to make sure that they are bias-free before we put them into production. So Besides everything that I just mentioned on the risk assessment, the review, and the bias testing, we also integrate explainability into many of our personalization AI solutions. And because there's no one-shoe-fit-all kind of solution, and plus, if you still remember, the generalist architecture that Lou just introduced actually is quite complicated. So by using some of the out-of-box solution, oftentimes we cannot get good explanation for our personalization AI. It turns out getting an explanation that makes sense is very important for our business owners within Verizon to adopt our AI solution. So they very much like to understand why the AI recommends one product versus another product so that they feel comfortable to use and adopt our solution. On the other hand, it's been proven like many times that our legal counsel are also looking at these solutions to make sure that they understand what trigger the explanation. So by building the explanation into our AI product actually helps our legal counsel to really understand and finally approve these products into production. And last but not least, I want to mention that there are often times we can see a working example that when we try to explain the behavior of these transformers and deep learning models, it came back with a lot of insights so that the data scientists can take and then to either fine-tune or reduce the feature space or add extra features to make the model learn better. So it's not just about helping with the legal review or helping the business to adopt the solution, but it's also about improving the quality of the AI solution. So here is just an example that I want to walk you through very quickly. So we are using a lot of inputs to the model, as Lou mentioned, like including the text, images, and the customer behavior in a sequence type of data. So here you see the model. At the end of the day, the model predicts the customer is going to purchase a Pixel 6a 128 gigabyte phone. And that is actually what they purchase. And then what this example shows is that there are actually certain clicks from the customers are actually positively contributing to the final output of the model. Those are not the last click by the customer. Instead, those are the second to the last and the fourth to the last clicks that positively contribute to the final model outcomes. So if you are just asking business people, then ask them to randomly guess which click is going to contribute the most to the output. They may randomly guess and they may tell you probably the last click. But this example shows you the model is actually not looking at the last click of the customer versus the second to the last and some of the previous clicks. So that helps people to understand why the model is recommending actually the Pixel 6a 128 gigabyte versus recommend the iPhone 11 64 gigabyte. So this is just one small example to illustrate how we are using some of the explainable AI capability that developed in-house to explain the GREC architecture that proposed by Lou's team. Okay, I think that concludes our presentation. Thank you.
Thank you so much. And I think we have time for some questions. So.
Hello. Thanks for the explanation, and it looks very interesting. I wanted to get your thoughts on what your team has experienced in terms of maintaining this large generalist recommender system. In terms of retraining and keep the data fresh, and in that vein as well, what have you observed in terms of maintainability, in terms of the cold start problem where you have new users coming in or new items adding in? Does that add to the complexity of having a large a generalist model rather than smaller models, or are there ways to mitigate that?
Yeah, sure. So I think handling the new kind of added item, added device, that's always some work needs to do there, right? So I think regardless of the newer implementation versus previously smaller, like multiple model approach, we all need to take certain action to kind of handling this new device launch, right? And I think one of the benefits here apparently is newer model means less model to support in production. So we have way less kind of independent pipelines repo we need to manage, right? It's kind of now we can have multiple team focusing on one or two kind of unified kind of repos. So it drastically simplifies, right, how we maintaining those kind of process to handle new device launch, right? And also I think some of the enhancement we did at the wide deep part, where essentially we kind of take the text description as well as image description to kind of form a warm-up embedding for the item. That also helps a lot, right? So even if, let's say, you have a new iPhone 15 launch, right? We don't have any behavior data about the iPhone 15 because it's new, but still, right? iPhone 15 looks like 14. The text description is very similar. Specs also similar in some level. And also, if we look at some other metadata level, features such as manufacturer, price, those are very similar. The point here is that also helps a lot, right? Even if we don't immediately retrain the model, it can still behave reasonably well, right, for those new devices using those technical we added in the direct. So, yeah.
How's it going? I was curious about the, I guess, like kind of system performance of like the model architecture with all the, the kind of wide and deep and like the sequence transformers and all that other stuff. Like, what does that kind of like end-to-end latency look like, and what do you have to kind of deploy that type of model on? Yeah,
it's actually, it's actually manageable, right? In terms of the model is big. However, with this task-based routing strategy we mentioned, we're able to just pick whatever we need and deploy, right? So we don't have to deploy the whole model into the use case. We can just pick certain expert, right? Because if we already know the task, we already knows which expert the task is going to choose, right, based on this step. So we only picking those experts, right? So if you think from that perspective, it's actually not significantly larger than the previous, right? Because we are not deploying the whole model, right? So to answer your question, this thing can run in perfectly fine on the CPU-based, right, like clusters, right? So and kind of latency-wise, we're talking about 10, 15 milliseconds kind of inference speed. So it's fairly manageable. It's not like we have to completely upgrade the whole inference platform to the GPU to handle this. It's actually way less expensive than some, let's say, right, in this case. So yeah, it's fairly manageable.
Okay, so I'm actually a little curious about, I guess, the item embeddings. So what's the performance difference from before you added image, like the same model but without image and description? And also, is there any performance difference if you like take out item ID?
Yeah. I think item ID still plays a more important role there, right? For those hot items, like let's say iPhone, Samsung, Google devices, right, and some smart home device. It's like that still plays a significant role there. One interesting we find is adding those description, right, and text significantly improve for those less popular items, right? Let's say some item user do not interact a lot, right, compared to some popular item. Those items, typically when we do accessor recommendation, it kind of like falling apart a little bit, right? It's kind of pulling something not super relevant, right? To recommend. But by adding that, it helps a lot, right? So it's like for the popular item, I think that helps. It's a little bit, but for the less popular item, this actually helps a lot, right? To essentially allows model to react reasonably well, right? By using those text and metadata and image-based features. So yeah.
I think last one, and then.
Thank you for the presentation. How do you incorporate A/B testing in your recommender system to make sure you get that entropy?
Yeah, sure. So we kind of looking at from multiple perspective, right? One is obviously offline. So we have TensorBoard integrated into our whole training pipeline. So as we run the retune, we kind of capture each rounds in the TensorBoard. So that's kind of offline metric-wise. We have those to use for comparison, right? Like what parameter works, what doesn't, right? And how does that compare to the older model, right? So we can use that TensorBoard to evaluate offline. Online-wise, we do standard A/B testing, right? So basically, we have different Strato labels assigned into different model, right? And in production, we kind of randomly distribute a certain traffic into a certain version of the model, and we run at a fixed period of time, and essentially running significant tests, right? And once we conclude something performed better, we get rid of the previous kind of whatever loose with a newer baseline, and we just continue iterating on top of that. So yeah.
Cool. I think we're at time, so thank you so
Thank
much,
you.
and we can take the rest of the questions offline.
Thank you.
Thank you.